And I don't even hear the announcement, so hopefully it's working. All right, so welcome to the Tutte Colloquium, the first Tutte Colloquium of this new term. So we will have Ross Kang as speaker today. Ross had his PhD from Oxford in around 2008, if I didn't remember wrong. And afterwards, he did and postdoc from McGill University and a few others in Netherlands. And currently, he's associate professor at Radboud University, Nijmegen. So Ross works on probabilistic and extremal graph theory and graph coloring. And today he's going to talk about some recent results on graph coloring, I think. So welcome, Ross, and please take it over.
Thanks, Jane, for the kind introduction. Yeah, I'm honored to speak at the Tutte Colloquium, and I'm very grateful for the invitation to speak here. But let me first embarrass myself with a sort of archaeological mystery. This was what I believe to be my last talk in Waterloo, and maybe you can take some clues from the pictures and try to figure out when this was taken. Okay. In case I forget to do so later, I'd like to acknowledge the collaborations with Ewan, Francois, Remy, and Jean-Sébastien. Yeah, so I'm going to be talking about independent sets and colorings in locally sparse graphs today. But before I get into things, I'd like to go through maybe some underlying themes or ideas behind my talk. So first off, there's this kind of vague paradigm about going from local to global in mathematics. And of course, this has its manifestation in combinatorics in terms of triangle-free graphs. So triangle-free graphs have been long studied in combinatorics and have influenced the development of combinatorics for over a century. And the basic question that one asks is, what kind of global graph structure can we obtain from under the assumption of some local structural conditions, such as having no edges in any neighborhood? In other words, having a triangle-free graph. So, right, this is like a local to global kind of idea, and it has a long history in combinatorics. For instance, Mantle's theorem is the basis for extremal graph theory from 1907. And we also will talk about Ramsey numbers in a moment in more detail. And this is also can be thought of as looking at global structure in triangle-free graphs. And then there's the obligatory mention of Tutte, who looked, among others, who looked at, for instance, the chromatic number in triangle-free graphs. And all of these foundational studies have been the root of fundamental areas in combinatorics. And this talk today will also fit within this paradigm. So we'll be looking at what kind of global structure we can gain from local conditions. Okay, another big theme in this work is, of course, the probabilistic method, which is one of the central methods in extremal combinatorics, but also in many other fields. And it just has this very simple, almost tautological principle. So the idea is that if you would like to find some nice object, so nice meaning having some prescribed combinatorial structure, then it suffices to set up a probability space over all possible objects and show that your structure is satisfied with positive probability. And so, yeah, this is almost tautological, but it has proven to be very powerful and versatile. And one of the key tools within the probabilistic method is what is known as the Lovász local lemma. Okay, so first off, just think about a collection of n mutually independent events, bad events, with some uniform probability of occurring at most p. So what's the probability that none of these occur? Well, of course, by independence, you just take the product of the probability that they don't occur. And this is at least 1 minus p to the n in this case, which importantly is positive. Okay, that was supposed to be a quiz that you could have easily answered. Okay, so but the idea of the local lemma is that with sufficient local control, so local conditions, then we can still have the same conclusion. So we can still have a positive probability that none of these events occurs. So there's this Lovász local lemma, which was published in 1975, which says that if you have n bad events with probability at most p of occurring, and each such event is mutually independent of all but, say, a bounded number d of other such bad events. And if you have that d is small enough in terms of p, then you still have positive probability for none of these bad events to occur. Okay, a third theme that we're going to try to bring into this talk. Okay, so it's a perspective from algorithms, from theoretical computer science. So the idea is, what if we're looking for what if we're really looking for a combinatorial object with some nice property, so a so-called flawless combinatorial object, and suppose that we're using some algorithm, so some randomized algorithm that can only make local changes at each step of the procedure. So in the past 10 years, there's been some breakthroughs in understanding the theoretical limits of such algorithms. And in particular, Moser's entropy compression method, which was devised to prove the constructive form of the Lovász local lemma, has had profound implications on algorithms and combinatorics. Okay, and a fourth kind of broad idea or theme that I want to try to link in together is the so-called hardcore model, which has its inspiration from statistical physics. So this is just a cartoon, and I'll hopefully be able to get into more detail about this towards the end of the talk. So yeah, hopefully by the end of the talk, I'll have been able to thread all these four themes together, or at least have given you an impression that they're linked. So well, let's just dive right into it. But yeah, if you have any questions, please don't hesitate to interrupt. Okay, so let's start at the beginning. Okay, so we're going to be looking at Ramsey numbers. So you probably all learned this in undergraduate, but let's anyway proceed. So RKL is defined to be the least integer n, such that if you have a complete graph on n vertices and you color each of its edges either red or blue, then you're guaranteed to have a complete graph on K vertices, all of whose edges are red, or a complete graph on L vertices, all of whose edges are blue. Whoops. So yeah, Ramsey was interested in this problem as sort of a side problem to solving some Hilbert problem in logic, but he proved that these numbers are finite for all K and L. This statement, this finiteness of the Ramsey numbers, is an example of a very vague but important paradigm that says in any large enough arbitrary system, you're guaranteed to find some highly ordered subsystem. And essentially, these Ramsey numbers help to quantify the most disordered system in this paradigm. Yeah, so I just wanted to flash this seminal paper of Erdős. You probably recognize it from 1947, which of course is one of the birth points of probabilistic combinatorics and random graph theory, even if it wasn't phrased in that way originally. But I'm not going to be, so here Erdős was concerned with the notorious symmetric case of the Ramsey numbers. But today I'm going to be preoccupied with the asymmetric case, the so-called off-diagonal Ramsey numbers. So I'll be interested in the parameter R3K, which again, I'll repeat the definition. It's the smallest integer n, such that if you have a complete graph on n vertices, each of whose edges is colored either red or blue, you're guaranteed to have a triangle which all three edges are red, or a complete graph on K vertices, all of whose edges are blue. And just to make sure that we're all on the same page, I'd like to reformulate this parameter. And okay, so here's going to be a running example, just a toy example. It's important to note that this toy example has no triangles. There's no three pairwise adjacent vertices. Okay, of course, we're going to be looking for independent sets in graphs. So that's a set of pairwise non-adjacent vertices. And it's important to remember that in a triangle-free graph, when you take a vertex and look at its neighborhood, that neighborhood is an independent set. And we're also going to be looking at the size of a largest independent set, which will, as usual, denote by alpha. And alpha in this particular toy example is 4, and there's 5 independent sets of size 4 in this graph. And so when we're looking at this definition of R3K, we have some red-blue colored Kn. Well, we can let the red edges induce a graph and call that G. Then the blue edges will induce the complement of G. And then you naturally have this alternative definition of R3K. So it's the least number n, such that whenever you have a triangle-free graph G on n vertices, then it's guaranteed to have independence number K or greater. So in other words, it's guaranteed to have an independent set with K vertices. Any questions about this part? Hopefully everyone's with me. So let me just give you a quick rundown on the state of the art of R3K, at least in the asymptotic setting. So the first breakthrough on R3K was by Tutte Colloquia and Semeredi in 1980 or 81. who showed that R3K is of order K squared over log K. And then shortly thereafter, Shearer tightened the asymptotic constant to 1. This paper by Taikomoshi Temery was actually the first use of the so-called semi-random method. And so that's really the state of the art for upper bounds on R3K. So Shearer's bound has not been improved for almost 40 years. On the other side, it's a more recent achievement, well, 2 tour de force of Bowman and Kivash, and independently Fitz-Ponteveros, Griffiths, and Morris, who improved on the work of Kim to show a lower bound of order K squared over log K, the same order, but with a precise constant 1 over 4. So there's a gap of about 4 between these upper and lower bounds, and this is the state of the art. And what's really cool about this this recent work is that they showed this using a very natural random graph process called the triangle free process, where you just take n vertices and look at all possible n choose 2 edges in some arbitrary order, random order, and just start taking them one by one. And whenever you encounter a triangle, you don't accept that edge, you just throw it away and keep going in the ordering. And they managed to analyze this process and analyze its independence number in particular in order to achieve this result. And they really threw a lot at it, right? So they analyzed some huge system of differential equations, and you used very sophisticated differential concentration inequalities to achieve this result. And this is the state of the art for R3K. I just want to note that it's a really easy, greedy argument to see that K squared is an upper bound, right? So if you have a vertex of degree K, you're done. Otherwise, you start taking vertices one by one and throwing away their neighbors, and that's how you get K squared. So this log K improvement is it's subtle, but it's very important. Okay, so what I'm going to be focusing on in this talk is actually this upper bound of Shearer, so that R3K is asymptotically at most K squared over log K with a constant 1 plus the low 1. And by almost the same argument that I just flashed by you about the greedy algorithm, this upper bound is actually the hard part of this upper bound is really in finding a good lower bound on the independence number for triangle free graphs of bounded maximum degree, say delta. Because again, if you have a vertex with degree K, you're done. And otherwise, you can apply this lower bound on alpha, and this is how you can obtain an upper bound on K squared over log K for R3K. So I'm going to be focusing on this particular lower bound on the independence number and many of its strengthenings and generalizations. Oh yeah, one thing I should mention is that this bound, as stated, this bound on the independence number, alpha at least n log delta over delta, is sharp up to a factor, asymptotic factor 2 due to the random delta regular graphs. So random regular graphs have independence number roughly twice this bound. And so that means there's still room to improve Shearer's bound. But remember, the gap on the previous slide was 4. So it would only, even if you could improve this by a factor 2, you would only get halfway to settling the asymptotic value of R3K. And I think there's some bets flying around about what might be the right value. But today, okay, so I want to focus on this bound on the independence number. And yeah, I want to ask maybe, yeah, sort of a fundamental question, say, is can you prove this with the vanilla probabilistic method? So let's write I, curly I of G for the collection of independent sets of G. What I'm asking is, can you find a nice probability distribution over I such that you can easily prove a random independent set from this distribution has the right expectation? Right, so if you could have such a nice probability distribution, then immediately from one application of the probabilistic method principle, you would be done. You would prove Shearer's bound immediately. And okay, so the answer to this question was already known. It's due to Davies, Jensen, Perkins, and Roberts. But what I'd like to show to you by the end of this talk, hopefully, is a slightly stronger form of the answer yes to this question. And the slightly stronger form in which I'd like to show this to you is in terms of the fractional chromatic number, which may be familiar to many or all of you. But let me refresh your memory. So essentially, the fractional chromatic number is about fractional vertex coloring, where okay, you still want that adjacent vertices have different colors, but you're allowed to use fractions of colors per vertex. And then the fractional chromatic number chi f will be the least amount of color that you use in total. And so for this running example, say we use weight half on each of these maximum independent sets of size 4. Then the amount of color we'll use is 5/2, and that's optimal. And it's slightly less than 3, the chromatic number. So you probably all know that so I didn't give you a very good definition of the fractional chromatic number yet, but you all probably know it. But there's so many different versions of it, right? There's you could know it as, say, the linear relaxation of the IP for a chromatic number, or you could think of it in terms of multicoloring, or you could think of it in terms of weighting, as I showed you on the slide. But for the purposes of this talk, I'd like to define the fractional chromatic number formally in terms of probability. So the fractional chromatic number of a graph G is a most K if there exists some distribution over the independent sets such that a random independent set from this distribution has some uniform occupancy guarantee. So every vertex in the graph has a probability at least 1/k of being in the random independent set. Or in other words, its chance of being occupied is at least 1/k. So if if we have this condition, then the fractional chromatic number is at most k. And the reason that this is stronger than what we need to answer yes to the question before is that we can use linearity of expectation by adding up over all vertices. And then we can find a lower bound on the expected size of a random independent set from this distribution as being at least n over k. And so if you can get an upper bound on k, you get a lower bound on the independence number. Any questions about this definition? Okay, so what I've been kind of leading you into is this sequence of structural parameters on a graph G that on one side has the clique number omega, then it goes to the independence number, or the kind of inverted form of it, which is called the Hall ratio, and then goes to the fractional chromatic number, which I just defined to you, and of course the chromatic number, and then the maximum degree plus 1 on the far right of this sequence. So this is sort of a cheat sheet for people in combinatorics and graph theory, right? This sequence of structural parameters, and there's more parameters that I've kind of left out, but anyway, let's see what this looks like for triangle-free graphs. So I'm now restating Shearer's theorem in this inverted form. So n over alpha is at most delta over log delta for any n vertex triangle-free graph of maximum degree delta. So this is hopefully what I will prove to you in a stronger form. And I want to mention a really remarkable breakthrough of Malloy from a few years back, who showed the same bound for the chromatic number. So he showed that the chromatic number, in fact, the least chromatic number is at most delta over log delta with this precise asymptotic leading constant of 1 for any triangle-free graph G of maximum degree delta. So this, okay, so first of all, this improved on a seminal result due to Johansson from the 90s, which was, didn't have the right constant, and it used a very, but it did have a constant, but and it used a very elaborate semi-random method. What Malloy achieved was not only a nice constant, which matches Shearer's bound, but also used a very, very beautiful proof method based on entropy compression. And shortly afterwards, Bernstein also slightly simplified Malloy's proof even further with the lopsided local lemma. Okay, so what I would like to tell you about today is the same result, but for the fractional chromatic number, right? So I would like to show you that the fractional chromatic number has this same asymptotic upper bound for triangle-free graphs. And now you might ask, so this is also later work. This is after Malloy and Bernstein's work. And so you might already ask, so why, Ross? What's the point? Well, okay, hopefully what I'll be able to show to you by the end is that the proof that I'm going to give you is quite simple and conceptual, dare I say, elegant. And for us, it's important that it was sort of a gateway to show us how versatile the proof method is, and could give us a hint of a much broader set of applications for the same technique. Okay, so let me tell you a little bit more about this. this different technique. Okay, so it's based on this so-called hardcore model, which sounds intimidating, but hopefully I'll show it that it's not. Okay, so the hardcore model is okay. It's probably nothing to do with these this cartoon. It's a probability distribution over the collection of independent sets of G, which is very, very nice. So, but more formally, the hardcore model is defined according to some fugacity parameter lambda, some positive lambda. And it's defined as a probability distribution over the independent sets of G, such that for any given independent set S, the probability of taking this set S is proportional to lambda to the number of vertices in S. So in other words, I wrote that the probability of a random independent set from this distribution being equal to S is equal to lambda to the size of S divided by some normalizing factor to make sure that the probabilities add up to 1. And for those of you who are doing algebraic combinatorics, this normalizing factor Z is also called the independence polynomial. And so for those of you who know more about the independence polynomial, the hardcore model is essentially equivalent to it. And why is this distribution nice? I keep saying that it's nice, but why? And this slide will be the kind of central part of the talk. This is the nice aspect of the hardcore distribution. So please pay attention. Right. So first of all, I'll give you some notation that actually I've kind of already given a little bit of. So if you have some arbitrary set, independent set S, let's say that U is occupied by S if it belongs to S. And let's call this vertex U uncovered if none of its neighbors belongs to S. So in this cartoon in the middle, these sort of bigger black vertices, those ones are occupied, say. And the small black vertices are covered. And the two big white vertices are so far uncovered. Okay, so let's take I from the hardcore model with parameter lambda. And then let's take some set X. So let's say this bubble here is X. This bubble here is X. There's some subset of the vertices of the graph. And let's reveal our random independent set, but only outside of X. And then let's look at the set U of U sub X, which is basically these two vertices here. These two big white vertices. U of X is the externally uncovered set of vertices based on X. So the property of the hardcore model that's very nice, which is called the spatial Markov property, as you probably guessed from the title of the slide, is that if you now reveal I within X, then it's the same as the hardcore model on U of X. at fugacity lambda. So in some sense, what it means is that there's independence between what's inside this bubble and what happened before outside of the bubble, conditioned on what you've occupied, or sorry, covered. So are there any questions about this this slide? So okay, let's okay, hopefully by the end of the talk I'll have been able to illustrate the power of this property. But let me first discuss the framework that we've developed around this spatial Markov property in the hardcore model. And it's something which we call the local occupancy method. Okay, so the local occupancy method is based around establishing a certain property of the hardcore model on G, which is called local AB occupancy. And so local AB occupancy is defined in the way that I've written on the slide. Okay, so it's that for every vertex and every possible induced subgraph of the neighborhood of that vertex, you have that A times this quantity plus B times this quantity is at least 1. So I don't expect you to digest this all at once, but what I would like to highlight is that if you take F to be the whole neighborhood, then what this basically translates into is the probability that V is occupied. And what this term translates into is the expected number of occupied neighbors. And so that's where this name local occupancy comes from, is that we're getting some bound in terms of A, B, and some occupancy probabilities being at least 1. And this method pivots around establishing this property for the hardcore model. And the method has essentially 3 different components. So component A is that for basically any, well, okay, not any, but for many natural classes of local structure, if we have a locally structured G, then we can establish this property. We can establish local AB occupancy for some specific A and B, depending on the parameter lambda and the maximum degree delta. And we can do so using the nice properties of the hardcore model. And this, okay, component B of this method is that if you have such a property for the hardcore model, then then you can transform it into another probability distribution that certifies that the fractional chromatic number is at most A plus B times delta. And this is the gateway. Okay, so right, so if you can find this type of property in terms of A and B, then you automatically get an upper bound on the fractional chromatic number in terms of A and B. And this component, while it's very important, it's also very simple, and it was also known before. So it was actually observed already in an ad hoc sense by Malloy and Reed when they were looking at Reed's conjecture and establishing it fractionally. But we kind of noticed that this has more general purpose implications. And the third component of this method is a slight strengthening of B in terms of the chromatic number, where we get a slight loss. So we get this log delta factor and this 1 plus epsilon factor. And also we also have some mild conditions, but roughly speaking, we still get the same bound on the chromatic in terms of the chromatic number or even the least chromatic number. And so again, if we get this local AB occupancy property established, then we automatically get bounds on the chromatic number. And because these extra terms are kind of small, they're essentially of the same quality as the bounds that we get automatically from the fractional chromatic number. And so what these three components together tell you is that essentially, if you want to get a good bound on the chromatic number, it suffices to minimize A plus B times delta subject to this property of local occupancy, local AB occupancy. And I'll show you some applications later of what kind of results we can obtain. But just a very quick word on how do we prove C. So I mentioned that Molloy's method relied on the entropy compression method, and Bernstein's relied on the lopsided local lemma. But actually both further relied on nice properties of uniformly chosen independent set in a graph. And a uniformly chosen independent set in a graph, I should have mentioned, is already is just lambda equals 1. And what we noticed is that essentially what we could do is input the general hardcore model into these proofs by Molloy and Bernstein. And this is how we could obtain C. So that's a very simplistic way of describing how we prove C, but okay, just an idea. Yeah, so we also could show some kind of algorithmic version using the stochastic local search framework of Akliopoulos, Iliopoulos, and Sinclair, which in turn relied on Molloy's entropy compression framework. Okay, so that was a bit of a technical part of the talk. Let me just run through some of the applications that we could obtain, or just maybe a couple of them for sake of time. So one important setting, a locally sparse setting, is the KR free graph. So yeah, graphs without a complete subgraph on R vertices. And there's this really long-standing and wide-open conjecture of Itai, Erdős, Komos, and Szemerédi, which asks for the same asymptotic type of bound as Itai, Komos, and Szemerédi for triangle free case to hold for all KR free graphs for any fixed R. This is still open, but there was some progress. There was lots of work on it by Scheer in the 90s, and then more recently by several teams, including some from the audience. What we could show is that we could tighten these bounds a little bit and get more attractive leading constants. Okay, we still don't know. Of course, Itai, Erdős, Komos, Szemerédi is still open. So, but these bounds fall out of the framework by nice properties of the hardcore model and some high school level analysis and optimization. And this is the state of the art for this. Oh yeah, and we also kind of refined the method of Bonamy, Kelly, Nelson, and Bostel by deriving both of these bounds from the classic Erdős-Szekeres bounds for the Ramsey numbers. Okay, I would like to skip a little bit to the setting of locally sparse graphs. Yeah, well, bounded local density. So this has its roots also in the work of Tutte, Semrady, and Shearer, which they pursued similar bounds in terms of the independence number. But there's this more famous work of Alon, Krivolovich, and Sudakov, who showed that if you have some limited number of triangles per neighborhood, say at most T, then you can get an upper bound on the chromatic number of the form delta over log of delta divided by root T. And this is a really nice generalization of the triangle-free bound. So yeah, it's a much more general result with many applications. And this was recently tightened a little bit by Akliopoulos, Iliopoulos, and Sinclair with their stochastic local search framework. And what we could show, again, with the hardcore method is a really nice leading constant for the same quality of bound, which matches Shearer's result in the case in the case T equals a half. You might notice this asymptotics here, but this is so if we don't want this asymptotics here, then we actually get into an yeah, I would have to give another talk. So the bounded local density case is also a very nice setting and has relations to the conjecture of Reed and also the Erdős-Nash conjecture. But yeah, okay, that would get me going for even longer than I. Yes, okay. But what's nice about this particular bound that we've obtained is that they match the quality of Shearer's lower bound on the independence number, and they're also sharp almost throughout the range of T up to a factor 2 and sometimes up to a factor 4 for some strange blow up reason. And this smoothly generalizes Molloy's bound on the chromatic number. Okay, Jane, I'd like to ask, I think I'm very close to being out of time, but how much time do we have left? Just to be sure.
Yeah, so usually it goes to 4:30 as an entire talk. So we typically ask the speaker to stop around 4:25. That's 3 minutes, but we start a bit later. So I guess if you go like another 5-6 minutes should be fine.
Yeah, sure. Okay. Yeah, then, okay. So I think that's, yeah, at least I can tell you how the basis for the proof works. Okay, so we want to, so I wanted to give you the whole proof for the triangle free case, because that's the classic case and it's also the most elegant part. So I was going to focus on this component A of this local occupancy method for triangle free graphs. And I'm not going to be able to give you the whole thing, but at least I'd like to tell you the basis for this, for these, for the proof. And the basis basically relies on two simple facts in the hardcore model for triangle-free graphs. And so one of the facts is this one. So the probability that a vertex is occupied, given that it's uncovered, is equal to lambda over 1 plus lambda. So again, we're doing a hardcore model with parameter lambda, and we're assuming that, so we're conditioning that V is uncovered. So why does this fact hold? So we're assuming that V is uncovered, then so it has a bunch of neighbors, but we know that none of, so yeah, we know that none of these neighbors is occupied in the neighborhood. And so basically, we're looking at the hardcore model on V itself, according to the spatial Markov property. And the probability that V is occupied in the hardcore model on exactly one vertex is just lambda divided by the two possibilities for V in the hardcore model on one vertex, which is just 1 plus lambda. Okay, so that's fact one. And fact two is that the probability that V is uncovered, given that it has exactly J uncovered neighbors, is 1 over 1 plus lambda to the J. So again, we have the neighborhood, and we have that there's exactly J uncovered neighbors. Let's say there are these ones. We need that all J of these are unoccupied for V to be uncovered. And because we are in a triangle-free graph, the probability of that happening is just the product of 1 over 1 plus lambda to the J by independence. And so establishing fact two really needs this triangle freeness. But using facts one and facts two, then, okay, it's a pretty short argument to prove local A-B occupancy according to B defined in terms of lambda and delta. You get this ugly formula. But okay, if you're a very sharp undergrad, then you can do this optimization. So you can minimize A plus B times delta subject to this ugly formula being at least 1. And then you will get this bound of the independence number being n log delta over delta. So I'd like to end with a few just open questions. But yeah, maybe this last one. So what I tried but failed to cover was a proof that if you take a uniform independent set in a triangle-free graph, and you look at the average size of such a set, then you will have this to be at least n log delta over delta. But if you would like to improve on this factor two, then what would be really great would be to look at this conjecture. Okay, so this is basically saying that you should be able to get twice the average size of an independent set as an actual independent set in a triangle-free graph. And if you could prove this conjecture, you would get a factor two in Shearer's bound. But okay, so I've already gone over time, and maybe I've confused you even more. But I'm really grateful for your your attention, and thanks a lot.
Thank you, Ross. It's a very, very nice talk and very interesting results. So let's see if there's any questions. Please unmute yourself and ask Ross.
Hello, I have a question. Yeah, sorry, my camera is broken, so I cannot turn it on. So you mentioned the results for KR free graphs.
Yes.
Yeah, so I saw the improvement. That's nice. I'm just like curious, like, do you think this? So why there is a gap between the current best result and the conjecture? Do you think it's because of the hardcore model or because some emphasis on the hardcore model? In other words, do you think the hardcore model reached the limits in this problem, or it still have some progress?
I think that, okay, so I think that it's hard to show this, right? Because we don't have there's no way of so we do have some hope of breaking through this barrier, but it's really difficult. It's of course I mean, we seem to be reaching a quite natural barrier. We cannot go further. I mean, in terms of the asymptotic quality of the bounds that we're obtaining, we're just matching what people had gotten before. So it could be indication that the hardcore model has this as a barrier, like it's really a barrier, but it's hard to prove that as being the case.
Is that like the same barrier as you trying to use Scherer's lemma on the K4 free? I saw the formula you do for K3. It looks very similar to the Scherer's idea. Okay.
Yeah, it's based on the same the same lemma of Scherer from 95.
Okay. Okay. Thank you. Very nice talk. Thank you.
Thanks.
Thank you, Lina. Other questions? So Ross, maybe I would like to ask some questions regarding, I forgot the name, local occupancy method, where you say that there are 3 components to apply, ABC. So maybe I missed a little bit. Is it you're trying to say that you need to establish this AB occupancy in these 3 parts, and then you can, so what you describe in for instance parts B and C, that you get upper bound for the chromatic number. So that's the conclusion that you could get if you establish this AB occupancy. Is that what you try to say here?
So we, it depends.
Or you try to prove
we
it.
only need A and C. You only need A and C really, but B is like a halfway step that slightly easier to optimize.
And also from B and C, if I compare it, so the hardcore model is a specific construction of probability distribution of independent sets in this space, right? Yeah. So if you have C, then you actually find a probability distribution that satisfies what you describe in B. Why would you get a not as nice bound in C compared with B?
So for B, we usually are just doing it with the hardcore model anyway. So yeah, B looks a little bit more general, but it's in fact not. No, it's that I should have clarified that in this slide. It's because when I did the triangle free case, then we didn't actually need this strength informed of local AB occupancy for the triangle free case. When I was I should have it's a bit confusing. So There's a simplified form of local AB occupancy for this fractional chromatic number result, which doesn't require you to look at all possible subgraphs F. It only requires you to look at the whole graph, the whole neighborhood subgraph. And that's why I tried to. I should have simplified all of it, but that's why I said this, right? So when you look at F being the whole neighborhood, then it reduces to these two things, and this is enough for the fractional result. And for the fractional result, you don't even need a hardcore distribution. You can just have any distribution that has the local AB occupancy.
Okay, yeah. Sorry, I mixed it.
It's my fault. I think it's
and C is
yes.
C is the. So sorry, what is the L?
That's for list.
Oh, the list coloring. Oh, I see.
It's because Luke is in the audience, so I knew that you would.
Okay. Oh yeah, now I understand. It was actually for different bounds. I was just.
And maybe it should be a C for or DP, but yes.
Yeah, and also in the previous slides, I think in the head you mentioned this spatial mixing. So does this method has anything to do with the spatial mixing in the arguments or something? Yeah, the spatial.
Spatial markov.
You just want to describe this markov property.
Yeah.
One for
C uses the spatial Markov property.
I see.
So Molloy's breakthrough used the spatial Markov property. He didn't call it that, but he used Molloy and Brent. They used the properties of uniform independent sets. But the uniform independent sets, the collection of uniform collection of independents, that distribution is just hardcore with lambda equals 1. And okay, it's just so the hardcore model comes in more than one place. Well, yeah.
Okay. So when you go through like parts A and C, is the most work trying to find proper lambda such that you can verify this AB occupancy. Is that how the proof would go? Or?
Yeah. Yes, and the proper lambda is not always what you might expect it to be. So for instance, in the triangle free case, it's like 1 over log delta instead of something much bigger, which is really very surprising. But but it's
okay. So it opts for the small 1 over log delta. It opts for small independent sets then.
Yeah.
Okay. Yeah, thank you. Other questions? Well, we are actually quite over the time, so
sorry for my.
No, it's my problem too. So let's thank Ross. Let's just unmute and thank Ross. And we will continue discussions after I stop the recording.